Thank you, Davla. Let me introduce myself. My name is Ariel Asri of Toshiba Electronics Europe. I'm representing Toshiba on the MIPI board. I'm also contributing member to the APHY. Ido Cohen of Alliance and myself prepared this talk about MIPI A-PHY, laying the groundwork for MIPI Automotive SerDes solutions. I will present the first part about the system view of the APHY, and the second part will be presented by Ido. He will provide an overview of the APHY specifications. Let me start with the system view for the APHY. The automotive industry is in the process of major transformations driven by multiple factors that should result with safer cars and less fatalities and to CO2 reductions. This can be summarized by the CASE acronym for Connected, Automated, Shared, and Electrification. Connected, with the telematics units moving to 5G, connecting the car to cloud services similar to what is happening in other industries. The car is becoming an IoT object. Automated, with the vision of robot cars and the move to level 3 and automated driving. Still, we are not there yet. Today we are maybe at level 2, 2.5. The shared economy is applying also to vehicles with the emergence of new players and new business models, and the electrification with hybrid and electrical vehicles, where battery and charging technologies are becoming important. MIPI is supporting that case with standard specifications such as RFFE for connected, APHY, CSI2, and more for the automated. The new car assessment program regulation are driving the need for sensor and display adoption in a car. For example, in ADAS, surround view application is driving the need for multiple high data rate sensors. Then the information needs to be displayed to the driver after being processed. This is also driving requirements for display adoptions. So what is APHY? APHY is an asymmetric physical layer specification targeted for automotive SerDes for use in ADAS, autonomous driving systems, and infotainment systems. The version 1.0 supports data rate from 2 to 16 gigabit per second over 15 meter range, with a roadmap to support 24 and 48 gigabits per second. The MIPI CSI2 camera and DSI display interfaces are well-proven protocols and are widely deployed in mobile applications in over billion of devices, as well as in automotive. However, since these protocols are using PHYs optimized for use in mobile application with C-PHY and D-PHY, where the low power and low EMI are the driving requirements, these PHY have typical reach of about 30 centimeters. In automotive, a much longer reach of up to 15 meters is required. Furthermore, the automotive environment is very much different than mobile. Automotive applications have much more stringent requirements for EMC, robustness, reliability, and functional safety point of view. In order to reuse the well-proven MIPI protocols and the widely availability of devices implementing the MIPI interfaces, several proprietary SerDes solutions addressing the issue of the longer reach automotive channel have been established and are widely in use in cars today. With the increasing number of high-speed video link, in the car, a standard is required. And it is required in order to enable more flexibility for system integrator and to reduce the costs. That is what MIPI is trying to accomplish with the APHY. In the first deployment stage, it is expected that standard APHY bridges are used for camera and displays. Multiple vendors will be able to provide interoperable devices using a standard technology, the APHY. In a second stage, APHY could be integrated directly into the camera sensors or into the SoC, eliminating the need for a SerDes bridge, and by that bringing further down the bill of material costs. In addition to the CSI and DSI MIPI protocols, APHY will support also VESA DisplayPort and EDP displays. MIPI is the only standard interface to support native camera and display interfaces for automotive using CSI2 and DSI2 over APHY. Any other solution will require a bridge. So let's take an example of this rear view camera application. where the camera information are being transported to the ECU, and from there need to be displayed to the driver. The driver can then see if it can safely drive to the back and recognize there is a child behind the car. From safety perspective, it is extremely important that the image with the child arrives unmodified to the display of the driver so that he can brake in time. If by whatever reason the display was frozen, the driver could not recognize there is a child behind the car, and we think he can drive back safely, but this will be fatal. Similarly, also, when the camera image is frozen, this could be dangerous. Therefore, from functional safety point of view, it is extremely important to have an end-to-end protection. Such end-to-end protection cannot be realized only by the PHY. It involves the PHY and the protocol, so APHY and CSI2 and DSI2 protocol to enable an end-to-end protection. Therefore, MIPI has followed the requirement and the recommendation of ISO 26262 standard. APHY and all the associated protocol are specified in a way to enable system integration of MIPI devices in ASIL-B and ASIL-D systems. It also requires a very robust link that is suitable for a long-reach automotive use, with all the stringent requirements in terms of reliability, car noise, and EMC. The APHY features a reliable link with an extremely low packet error rate with 10 to the minus 19, meaning that a packet error can occur approximately every 10,000 car lifetime. It requires a high-speed downlink to support the aggregation of multiple 4K cameras and displays, while keeping low latency with about 6 microseconds at Gear 5. It does not help to have just a reliable link between the camera and the ECU, as these links are connected by cables. Some malicious person could insert something in between to tamper the image from the camera or the image going to the display. So another important requirement is to enable the such high-level end-to-end functional safety and security when using heterogeneous interfaces. For example, with different display protocol, such as MIPI DSI or VESA DisplayPort, EDP, or legacy OpenLDI, or using different PHY from MIPI like C-PHY or D-PHY on camera or SoCs. So all of these requirements make it necessary to have a well-optimized and aligned specification between the PHYs and the protocol for camera and display at the system level. And MIPI introduces the concept of MAS. It stands for MIPI Automotive SerDes Solutions, providing a vision for an end-to-end system where the end-to-end protection is realized always source to sink, from the camera source pixel to the sink, and from the display source to the sink display pixel. MIPI is supporting both MIPI and VESA display over APHY. And HDCP is used for display content protection where needed. So MIPI takes also care for the control path and all the sideband signaling as well, which is also very important. And this is what MIPI is aiming for with not only the APHY, but the whole collection of specification with standard protocols along with the APHYs. So how it all fits together into a clean layered protocol stack is illustrated in this diagram. At the lower layers, there is a common baseline with the APHY that include two sublayers, the PHY sublayer and the data link layer that is agnostic to each protocol, and Ido will provide more details later. The protocols are connected to the APHY via the PAL, protocol adaptation layers. MIPI is developing the protocol adaptation layers for an optimal usage of the PHY for each dedicated protocol, while taking also care for functional safety as needed. A common approach for MIPI A-PHY adaptation layer is being used across camera and display protocols. A common packet structure enables the support for heterogeneous interfaces for display with DSI2, DisplayPort, EDP, and OpenLDI. Also, provision for a mix of PHYs are considered by the PALs while considering functional safety, such as mixing C-PHY, D-PHY, or A-PHY on either side of the link, with SerDes, without SerDes. So on the top of the adaptation layer, we have the native protocols such as CSI2 and DSI2 and so on. Such protocol can be reused, and the automotive ecosystem can enjoy the benefits from further evolution of the mobile protocol. The end-to-end functional safety and security services are added on top of the CSI and DSI protocols with the camera service extensions, CSE, and the display service extensions, DSE, directly at the source and at the sink. The service extension contain the provision for common end-to-end services, such as functional safety, security, and HDCP for display. The display service extension are common and are commonly applied to VESA, EDP, and DisplayPort, as well as to MIPI. On top of the CSI2 and DSI2, you can see the command set protocol that are used for controlling the camera and display. And MIPI also prepare other additional protocol adaptation layer to enable the sideband signaling for low bandwidth I/O, like GPIO, I2C, I3C, and we will add more interfaces in the future. These are very important to have an overall system saving when having multiple protocol all tunneled on the same wire. And by that, I will now transit to Ido.
Thank you, Ariel. My name is Ido. I'm the APHY subgroup vice lead, and I've been involved in the activity of the APHY and other protocols within MIPI for a long time. And I'm also the director of strategic innovation in Valence Semiconductor. I will try to give the highlights of the APHY specification in the coming slides. And there's a lot of material, so let's start. First thing, as Ariel already mentioned previously, the APHY has supporting data rates between 2 gigabits to 16 gigabits, divided to 5 defined gears, 1 to 5, and we have one uplink gear for 100 megabit per second. There is one rate line code or modulation for each of the downlink gear, and we are supporting 2 profiles which are different by their noise and performance, noise immunity and performance. The 2 lower gears, gear 1 and 2, supporting 2 gigabit per second and 4 gigabit per second respectively, are a profile 1, and which means that they are optimized for low cost and power implementation, and relatively good or enough noise immunity to support packet error rate of 10 by -9. And the profile 2 is supporting gear 3 to 5, which is 8 gigabit per second, 12 gigabit per second, and 16 gigabit per second. And this profile is supporting much higher noise immunity levels, looking at the whole vehicle lifespan, and providing packet error rate of 10 by -19 for this type of noises. One comment regarding this compatibility: all devices supporting gear N, like gear 2, 3, 4, 5, need to support all gears that are below them, which means there is a backward compatibility and between gear compatibility for all devices. Another difference is that the net application data rate for the profile 2 gears from gear 3 to 5 is 90% of the PHY rate. The APHY is defined for single lane point-to-point over both coax and SDP shielded differential pair, and it supports delivering power over cable for both type of cables and supports up to 15 meter with 4 inline connectors. Definitions are part of the spec for this type of channels. The PHY itself, so the high-level structure, we can see there is the native protocols that previously mentioned by Ariel. Below them, there is the protocol adaptation layer, the PAL, which is unique or per native protocol, and it maps the native protocol to the A packet, which is the unit of the APHY. Between the packet adaptation layer and the link layer, which is the APHY, the upper layer of APHY, there is an APPI, which is the interface between them, and it's taking the A packets from the PAL to the link layer. The link layer, it performs the scheduling, prioritization, and forwarding of A packets to the physical layer. The physical layer, it's encodes and decodes a symbol extracted from the A packet according to the modulation scheme in a specific gear, and transmitting the modulated symbol over APHY according to the medium-dependent specification. You can see that the thick lines are representing the downlink, and the thin lines represent the uplink, which is in a lower bandwidth. Going into the PHY layer, so as described previously, there are the lower gear are supporting the NRZ 8-bit, 10-bit, and so the APHY has a unified structure to support both the PAM-X for the higher gears and the 8-bit, 10-bit NRZ for the lower gears. You can see here there is the link layer at the top, then a block called RTS sublayer, which manages the data pacing and buffering, assigning the message counter and CRC, which are required for the supporting the functional safety features of ISO 26262. And for Profile 2, it implements also the retransmission process of A packets. That this we will go into details in a few slides. Below that, there is the PCS layer, which is either for the PAM-X or for the 8-bit, 10-bit, and it specifies the conversion of the data link layer into PHY symbols. And in the Profile 2, it also handles the canceller, what we call just-in-time cancelers, which are cancelers that are only applied when needed in the channel changes or other elements which are defined in the spec. The PMD, of course, is the medium-dependent specification, and it's depending on a specific channel. As I said, RTS, retransmission, is a time-bounded local PHY level retransmission. Time-bounded, it means that the retransmission is attempted only within predefined overall delay. The overall delay is defined here by the green lines, saying it takes the time from the link layer to the TX, then the interconnect delay, and then the RX delay. All of these are calculated for overall delay, and this delay is maintained by the retransmission mechanism. As you can see, the retransmission is at PHY level at the link layer end. It does not observe or does not impact any of the higher level layers. So it's transparent for the upper layers. And it happens between single hop of APHY. Dynamically modulated means that the retransmitted packets are being sent over a better error-resistant data payload and subconstellation. It provides highly reliable data with packet error rate of 10 by -19. It's highly resilient as it allows the system to overcome 1,000-symbol long errors with burst, which is very common to the automotive environment, and it can overcome multiple tens of millivolts pulses as instantly attacking. Again, very common at the automotive environment. Last thing, it allows us to have a very low overhead, which means that the overhead of the PHY and the link is only less than 10%, which provides 90% net data rate of the PHY rate. The data link layer is the next layer, is enabling the protocol or the PHY to work with protocol agnostic definitions. It performs scheduling, prioritizations, and forwarding of the A packets. Each protocol adaptation layer here has at least one APHY connection to the APHY data link layer, and the APHY data link layer can be connected to multiple protocol adaptation layer using single local function, which is mentioned here. The APHY data link layer may have a single APHY network PHY, single or multiple ones in case of specific use cases. So again, this data link layer enables the APHY to the forwarding, prioritization, duplication in some of the use cases, and scheduling of A packets. From functional base safety, as mentioned again by Ariel, APHY is planned to support functional safety goals of automotive. It is having the recommended measures to support the ISO 26262 2018. We have a CRC 32 for each packet, providing homing distance of more than 3 and a message counter of 8 bits, and also implemented as in the system is a timeout monitoring to fulfill keep alive function. These allow us to argue a diagnostic coverage for communication bus per table D6 in the ISO definition. The upper layers or functional safety features for a specific system level safety goal like ASIL B or D is expected to be managed by the upper layers. From noise immunity, so there is a major variance in OEM EMC requirements, from those who aim for minimal noise immunity to OEM that apply stringent requirement to their system. This is why APHY introduced 2 profiles to provide 2 noise immunity levels and accommodate this variance. The profile 1 has a lower noise immunity, and similar to what you can find in current SerDes, and it's supported for Gear 1 and 2, and optionally for Gear 3. In P2, profile 2, it has a very high noise immunity based on the analysis of expected noise levels in car lifetime period. MIPI as a group and the APHY subgroup with the automotive subgroup in MIPI conducted independent tests in various labs, evaluating the noise levels and the shielding effect degradation after mechanical stress and aging. The results helped to evaluate the different available technologies, and the research continues now as part of the MIPI A-PHY subgroup activities. This is an example of what we've seen in the tests. What you can see here mainly is the difference in the screening attenuation of a coax cable between before and after applying the bending testing and stress test. So before we finish, so MIPI, the MIPI A-PHY version 1.1 is now under work in the APHY subgroup. It's an incremental version of the APHY 1.0. The APHY 1.1 will allow up to 32 gigabit per second throughput using dual lane downlink support over STQ cables. It will double the rate of the uplink to 200 megabits per second and improve the net data rate to 125 megabits per second. And it will allow to add an option of PAM4 supporting the lower gears, gear 1 and 2, to have better noise immunity with low working frequencies over lower cost cables and connectors. And we are adding an additional protocol adaptation layers for 100 megabit per second Ethernet and for I2S. So in-vehicle architecture is rapidly evolving, as we've seen today. The increased focus on surround sensors and application for ADAS autonomous driving is best served by dedicated high-speed asymmetric interfaces from the sensors to the ECUs. The standardization is important for economic of scale and lower cost and greater capabilities. And the MIPI native protocols like CSI2 and DSI2 with the APHY deliver enormous benefits to the automotive industry in means of performance cost, noise immunity, and long-term EBOM reducing. The MIPI solution is being developed to meet the broadest spectrum of automotive industry needs with anticipated SOP as early as 2024. Thank you very much. I hope this was interesting, and now we are open for Q&A.
Thanks, Ariel and Ido. Appreciate that. So I encourage questions to come through the Q&A pane. Please go ahead and type your questions, and we'll get to those momentarily. Meanwhile, I do see a question that has come in. What are the strong points comparing LBDS or other SerDes?
Thank you for the question, Derba. We don't have much time, so I'll try to make it very quick. So I think, first of all, it's the standardization versus using a proprietary solution. I think it's very clear that the standardization will bring a better ecosystem, and in the long term, reduce the overall cost for the whole environment. Second thing is the MIPI A-PHY brings noise immunity capabilities that are not available today, and it will allow system to adequately accommodate noise levels in the whole lifespan of the system. And I think the third one is very similar. It is a packet error rate of 10 by -19. That's literally saying almost no error to the lifespan of a car, and with enabling 90% net data rate from the overall throughput of the PHY. The last thing is that I think it's another important aspect is that it's fully hardware stack. There's no software stack required for these solutions. So it will allow us to have very efficient and power efficient and size efficient systems.
Thanks, Ido. We do have just a few seconds left. Does the APHY spec cover communication link requirements, for example, S parameters?
So yes, the APHY specification defines the link requirements end-to-end, including return loss and insertion loss. And there are also within the MIPI members that share the channel model for simulation between the companies.
Okay, thanks, Ido. Apologies, we're out of time. I do encourage the audience to move over to the next session by clicking the CTA call to action, and you can see the agenda and upcoming. Thanks, Ido. Thanks, Ariel.
Thank you.
Thank you.